Okay, good evening, everybody. I apologize. I thought I was going to be a little bit late. I knew it was kind of close, so we're starting here on time, so it worked out okay. We are already, believe it or not, in week 10 of the semester, so I really don't have a whole lot of more material to go through. Tonight we'll finish chapter 6, review some of the homework, and we'll move into chapter 7, which is forecasting, which I think is an awesome chapter just because, it doesn't matter where you work, you try to forecast things. Whether you try to forecast, the budget, the sales for next year, how much inventory you'll need. Almost every job has some kind of forecasting aspect in it. So we're going to learn some techniques for forecasting today. We have the next week, we will go over, I think we're going to skip on to chapter 9, which is queuing analysis. That is like the study of queues or waiting in lines. We'll talk about that. That is week 11, I believe. And we are coming up on our final assessments. We have a final projects due on the last class, which is, I think that's Thanksgiving week. And our final exam is week 13. So, any questions on the schedule, where we're at, where we're headed? Good. Okay. So what we talked about in chapter 6 is the art of decision making, and we talked about a couple things. First off, the environments where we can make a decision, and there's a couple environments. One is certainty. That means we know what's going to happen. And we really, there's some things we could do with that, but that wasn't really in the scope of what we covered in this chapter. So what are the two environments we talked about? When we have no clue what's going to happen, we don't have any knowledge, we can't assign a probability to what's going to happen, what do we call that? What do we call that environment? That's uncertainty. We have no clue, right? If we can assign a likelihood to a future state of nature that may impact my decision, we call that what? We call that kind of decision, what kind of environment do we call that? Risk, okay? So we said we have different methods for decision analysis depending on what environment we're in. And we talked first about uncertainty. And we said uncertainty, we don't know what's going to happen. Using a payoff table where our decision alternatives are on the rows, our future states of nature on the columns, mutually exclusive and exhaustive. We can use something called the max and min, where we pick the best of all the worst case scenarios. That fits a pessimistic or conservative investor. We're trying to lock in some minimum. We can do another pessimistic or conservative approach, which is called min and max regret. But instead of looking at the payoffs, I'm trying to look at lost opportunity, right? So I'm trying to pick the minimum of the maximum regret. So, if I don't do this, well, I could feel a lot of regret, and I want to minimize that. So that's min and max regret. One, if it's an aggressive or optimistic investor, max and max, I pick the highest of the high. And then finally, one is kind of in the middle, is the principle of insufficient reasoning. So that was the kind of the first approach that we used. And then we said if we can assign likelihood to it, well, that's important, right? So not only is the payoff important, but how likely that payoff is to happen is important. And we uncovered or discovered or spoke about one of the most important decision-making theories in business world, and that is expected value theory, right? Very simple formula. We take all the possible payoffs times the probability of those. So we're weighting those two things, together, right? And we talked about, hey, the insurance industry is founded on that. The whole financial services industry is founded on that. The gambling industry is founded on that. Deal or no deal is founded on that. So many things you think about, expected value is part of that equation. We also did a little exercise where we said, if we only did things according to expected value, well, we'd never insure our home, we'd never insure our car or our lives, we would never play the lottery, we would never gamble. Life would be kind of boring, it sounds like, right? But there's a difference between expected value and what was the other thing? There's a reason we do all those things. What's that? No, because value is kind of the payoffs. But we look at utility, right? The usefulness or the happiness that we generate from those payoffs, or the payoff of a bad payoff. Now, the one I wanted to do, because I don't think I really covered this very well, is number 20. We can do others, but I thought number 20 would be a good one to do, because it kind of deals with a little probability concept that you may have known how to do, or maybe not. I signed number 20, right? Yes? Yes, okay. Oh, don't tell me this document. Oh, there we go. All right, Marriott Hotels is planning to build a new hotel property in a suburb of Portland, Oregon. The company is considering one of 4 sizes of hotels to construct. Smallest to largest, you see them there. Construction will take a year to complete. Profitability of the property will, to a great extent, depend on whether an industrial park or a university is developed in the area. The following table gives a long-term present worth profit in hundreds of thousands based on the size of the hotel constructed and the development that could take place. So what it's saying here is if we build a 120-room hotel and industrial park comes, we're expecting 2.2 million would be the net profit for that thing. If we build a huge hotel, 330 rooms and no development happens in that area, that's going to be a bad thing. That's a $1 million loss. So it says Marriott Management estimates that there is a 60% chance that an industrial park will be developed, a 30% chance that the university will be developed. The two developments are believed to be independent of each other. Determine the optimal size hotel Marriott should construct based on the expected value. Okay. So we really have a decision making under what? Uncertainty or risk here. What do we have? Uncertainty or risk? We have risk, right? We have some likelihood of those events occurring, but we have 2 independent events. It tells us the probability that there is an industrial park is 60%, and the probability of a university, is that a university? 30%. Universities just don't spring up too often, but I guess some of the for-profits do, is 30%, okay? But if you look at it, I have 4 future states of nature. Neither happens, industrial park only, university only, and both. So how do I go from here to here? How do I go from these overall probabilities to the combinations? Any ideas, any thoughts? No? Okay, well, we're going to use a mechanism, it's called a multiplication rule, but it's also called a probability tree. And you may have remembered it if you took me for Stat 301. Because these events are independent, we can look at them that way. So we can kind of draw first, and it doesn't matter which one we draw first in this case since they're independent. Independent mean what? What does independent mean? What does independent mean? Independent events, what does that mean?
One does not affect the other.
One does not affect the other. If I flip a coin and I get tails, the odds that I get tails on the next flip is still 50%, right? They're independent. Coin flips are independent, meaning there's no relationship, right? Some people think there is, like, oh, you just got 9 tails in a row, so I'm going to go with heads. There's a better chance. No, it's still 50-50, but this is independent as well, just like a coin flip. The industrial park and the university aren't talking to one another. So we can say, the odds, and I'm going to draw a probability tree, the odds that the industrial park is built is 60%. So then what's the odds that it's not built? Let's go there. What's the odds that it's not built? 40%. And that's called, you don't need to know this, but you understand it to be so. That's called the complement rule, because if it's 60% chance of something happening, it's 1 minus that of it not happening. So the complement of an event is the event not happening. So I superscript C, that means I not happening, is 40%. Okay? So that's good. But if we take this tree and we go a little further, we can say, well, if we build an industrial park, So if we're here in this tree, what's the odds that a university gets built? Overall, because it's independent. It doesn't matter if we build an industrial park or not, it's still what? 30%. So if we build an industrial park, what's the odds that a university doesn't get built? Via the complement rule, still 70%. Okay. Down here, what's the odds we didn't build an industrial park? What's the odds we build a university? Still 30%. The odds that we don't build a university is 70%. Okay. So I want you to notice, right? This is called a probability tree, and it's a way to kind of envision sequential probability events or sequential events and then figure out the probability of those events. And there's really 4 occurrences here. Neither happens, an industrial park only, a university only, or both. And if we look at our tree has how many ends? It also has 4 ends, okay? And the way this works is if we want to know the odds of building an industrial park and a university, we're going to multiply along that path. So the odds of both building an industrial park and a university is 60% times 30%, and that gives us, if I did my math right, that's 18%. The odds that we build an industrial park but not a university would be 60% times 70%, or 42%. Do you guys see this? The odds that we build no industrial park but a university is 40% times 30%. That gives me 12%. And the odds that we build neither, no industrial park and no university, 40% times 70% is 28%. Now if I did this right, there's 4 outcomes. Each has a probability assigned to it. If I did that right, those probabilities should and do add to 1 or 100%. Okay? So does that make sense? That's what you use for sequential events. And if there was a third thing involved, an industrial park, a university, and let's say a shopping outlet, this would have to have 3 branches, right? It would have to have 3 levels to it, and the tree would get more difficult. We see, if I asked you flipping a coin twice, right? It's the same thing. We would say, hey, getting heads on the first flip is 50%, getting tails is 50%. What's the odds that I get, heads and heads? Well, 50% times 50% is 25%. Heads and tails, 50%. So that anytime we're doing like sequential events and we want to know the probability, we use what's called the multiplication rule, and we multiply along that path. So now this becomes pretty easy, right? Because we have, and I'm going to kind of skip ahead here. Now that we have those probabilities, and we know this is under risk, we can use on Blackboard under material by chapter. If I go to chapter 6. And we can use our payoff table template because we're going to use expected value. And I'm going to kind of cheat a little bit. Let's go to, just bring up 20. Because I don't want to bore you guys with me entering in all this data. But we have our 4 decision alternatives. We have our payoff table, which is given, and then we have down below the probabilities that we were given. So what it's doing is it's saying, for the 120, take 28% times 12, plus 42% times 22, plus 12% times 18, plus 18 times 30. And under this method, it's telling us to do what? It's telling us to do what? What should we build and why? Using the expected value theory, what should we build and why?
Hotels with 260 rooms.
Yeah, it's telling us build a hotel with 260 rooms, and our expected return is 2,700,000 or what? 2.7 million, I guess. 2.7 million. If I wanted to know exactly what would happen. Okay, if I want to know exactly what would happen, maybe I could, I don't know, bribe an official maybe that knew about zoning or something like that. That's not really an ethical order, for instance, university, but how much would, if I knew exactly what was going to happen, what would I expect that extra knowledge to be worth to me? To figure out exactly what was going to happen. What do I look to for that?
The EVPI.
Expected value of perfect information, which in this case would be roughly about $500,000, right? So, that tells me the expected value of having perfect information. That's what I'm expecting. Doesn't mean it's going to be worth that much. If that's a big number, maybe it's worth doing some research, if we can get more information. Now, if I didn't have any knowledge, let's pretend like I don't have any knowledge. We didn't have these probabilities. We were making this under uncertainty. And let's say I was focused on lost opportunity. What would I do? I didn't have any knowledge about the probabilities. If I was focused on lost opportunity, what would I go with? What decision would I go with there? If I was focused on minimizing my maximum regret, I would go with
Minimize regret.
Minimize regret, which is saying 260. If I was an aggressive investor, I would go with max and max, which is 320. If I'm very pessimistic, very conservative, it looks like I go with 120, which kind of makes sense, right? Now, if I leave this alone, let's say these probabilities changed, and there's a much better chance. Let's say this was only, I don't know, let's say this was 10%, and this is 10%. Let's say this is 10%. And the odds of both happening is 70%. Now it's leading me to build the big one, right? Build the big one, expected value 320, 4.9 million, roughly 5 million. Why? Why is that? Because expected value factors in not only the magnitude, but the likelihood of that event occurring. And now I give more weight to these big values. 65 is getting, 70% of the weight. So that's why it's forcing it down that way. If we're very pessimistic, maybe it's a pipe dream that both will happen. Maybe this is 10% and this is 70% down this end now. It's going to force it down the other end because it is responsive to the likelihood, just like you would be, right? Maybe one of the things that you looked at when you decided to get your MBA is there's expected lifetime earnings by degree. If you have a high school degree, do you know what it is? Your expected lifetime earnings are? What do you think it is? Just a high school degree period. Expected lifetime earnings is about 1.1 million. If you have a 4-year degree, that goes up to what? Do you guys know? You guys didn't look at these? Then why did you come to college? Just for the love of learning? It goes up to about 2 million. But if you get a master's degree, it goes up another, I think it's like 800,000, something like that. It's like 2.9 million. So, you may be paying opportunity cost to be here, maybe paying money to be here, but your expected lifetime earnings are going to go up. You guys never looked at those tables? I'll Google it and see if I can find it. Now the numbers will not be what I said they are. Expected lifetime earnings by education level. Let's see if I can find an image. Is that the column? Maybe that's wrong. I don't know, I thought it was about $1 million difference, but it's showing a high school graduate is about $1 million. I was right about that. Associate or bachelor's degree about 1.61 million. Master's degree about 1.93 million. Professional degree, doctoral degree 2.3 and 2.9. So that is maybe, what went into your decision about, getting a master's degree. The likelihood that you'll make more money goes up for sure. Okay, any other questions on the homework? Any other problems? No? Okay. Then let's move forward. All right, so in chapter 7, we're going to talk about forecasting models. Before we get into some methods to do that, does anyone forecast anything at their current workplace? No one? In the dark? No?
Forecast fuel and ammo.
Fuel for what? I'm sorry.
For trucks.
Okay. So what's the methodology used to do that?
Well, you get a certain amount of money, and then each truck is out for many amounts of fuel for mileage.
Okay.
Depending on emissions.
Oh, okay.
There's a
So,
lot of different.
so you know how far you're going. You know that this truck averages blah blah blah.
Right.
So you forecast how much fuel will need. Okay, that makes sense. Very good. So that one's probably pretty accurate method. Probably not a very hard forecast, right? How about what we're going to focus on this, and this is like a time series. Does anyone look at the past to try to look at the future? Yes? Eric, give me an example of this, which I know your office does this, right?
Whenever we're trying to figure out the number of students we can expect in the future, we usually look at the past 3 or 4 classes
Okay.
to get an idea of the total class and also per major.
Okay, so what do we have, like, how many, this year was a down year, but we had
Roughly, let's say 360.
360, okay. So very important at St. Francis University. We are like 90% tuition driven, right? So one of the numbers that's very important at St. Francis University is obviously you guys coming here, but also our freshmen coming here, right? So Eric works in our enrollment management. So we can look back historically at about how many freshmen came every fall, right? And we can try to predict that because that predicates, how much we'll have in the budget. Yes, that very important number to not just to people in enrollment management, but to everyone that works for St. Francis University. And one of the things that's even kind of more critical at a place like St. Francis University is if this was like quarterly sales, well, you might be able to make up for it the next quarter. But if you think about it, freshmen are sales for the next 4 years. So if we have a bad freshman class or a small freshman class, that kind of impacts you for 4 years. So we do forecasting based on a couple things, but historically is one thing that we look at, right? So what else? What else? Yes, Katie?
We do it a lot in classes, like you look at what it takes to win your place in your class and predict.
Okay.
See like who you want to go and what event.
All right, so very good. You can forecast historically in this meet, in this month perhaps, this was the winning time and this is what my person's running and this can earn me this many points. I'm sure there's a lot of strategy involved. I'm sure when you recruit track athletes as well, you can look at their performance, maybe their freshman year, their sophomore year, their junior year, and their senior year, and use that as a prediction, like how they're going to do in college. Swimming, I'm probably sure the same way. I know my brother-in-law is a track coach, and he actually even looks at like how they train, and if he knows if they don't train real well, but they're still running good times, hey, that's a good thing because there might be a big delta there, if they get under his tutelage or coaching. Very good. What else? What else? Is anyone else forecast? Yes.
I know people in other departments look at, they try to forecast like parts to keep in stock.
Okay. And how do they do that? How do they forecast it?
Historical, I think, plus some other.
Okay. So one of the big things that we're going to talk about, so historical is what we're going to focus on. There's other ways to forecast, right? There are ways we can forecast on other variables, but a big one tends to be, what's happened in the past is probably a good prediction of the future. Yes? That's usually a pretty good prediction of the future. Now, not always, right? There's sometimes, crazy things happen. Some events called like black swan events. Have you ever heard that term? Happen. But forecasting is the process of predicting the future, which is kind of cool that that's what we're trying to do. We're like trying to look into a magic ball, but we're using math to do that, right? We're trying to predict what's going to happen. It's an integral part of almost all business enterprises, and we kind of had that as an example here. We talked about universities and athletics and manufacturing. So service organizations forecast customer arrival patterns. Manufacturing firms forecast demand for the project or product. Forecast revenues. Has anyone ever, invested in stock? Analysts come out with estimates of, what earnings per share for the stock will be, and sometimes they miss those estimates. Sometimes they overreach those estimates. Firms consider economic forecasts of indicators, housing starts. All those things are very, very important. Now, if we forecast well, excellent. We can staff appropriately. We can order parts appropriately. We can recruit better. We can manage our team better. We can, forecast our revenue and budget accordingly. Our manpower. All those things increase customer satisfaction because we have the correct number of people on staff, or we're not out of parts. All those things can happen. Now, forecasting can be based on educated guess, and I never want to go away from that, because an educated guess is why we pay people, maybe considerable amount of money, because they have great expertise, and they can make educated guesses that are damn good. Okay, expert opinions. What we're going to focus on is past history of data values, known as a time series. If that's possible, hey, that is data that can lead to information, that can lead to knowledge. As we know, knowledge is power. So let's first talk about the components of a time series. And when I talk about time series, there are two types of data. There's time series data. That's data gathered over time. So when week 10 of the class, if every week as Katie walked into the room, I asked her what her mood is on a scale of 1 to 10, and I graphed that over the 10 weeks, that's time series data gathered over time. It can be data gathered over weeks, minutes, months, years, decades, centuries. Time series data is data gathered over time, as opposed to what's called cross-sectional data. Okay? If you think about what a cross-section is, if you think about the time continuum, if you take a slice in time, if I asked all of you what your mood was on a scale of 1 to 10 at this slice in time, that's cross-sectional data, like right now. Okay? Time series data would be gathered over time. So there are components of a time series. And the first one is something called long-term trend. And long-term trend is like looking at overall what's happening with this time series, from start to finish. Is it trending up? Is it trending down? Is it following like a stationary trend? Is it kind of going up and down, but it's not really, it's not really heading long-term up or long-term down? And is it going linear, or is it some kind of other function like quadratic or exponential? Like what's going on with this thing over long term? We'll talk about that. The second thing, which is very interesting, is seasonal variation. What do I mean by seasonal variation? What do I mean by, anyone working in retail understands seasonal variation very well. What is seasonal variation? Yes? Yeah, changes associated with the time of the year. And usually we're pretty good at forecasting that, right? We know, if you're in the retail environment, they call it, Black Friday for a reason, because, hey, we get, almost, 50% of our sales in November, December, and, that's important to us if we sell a certain product. If you are, some kind of retail operation in Greta, I think it's only 3, but, they are very much, they have seasonality associated with that. So any kind of changes tied to the calendar, if you're in the ski industry, or the lawn mowing business, the landscaping business, but almost all industries have some kind of seasonality associated to it, right? So Maybe our sales are up in June, but they're down in February. Well, if we can denote that, well, that's information we can use. When a repetitive pattern is observed over some time horizon, a series tend to have seasonal behavior, usually associated with calendar climatic changes, frequently tied to yearly cycles, but it doesn't have to be yearly cycles. I used to work in the banking industry, and our bank had cycles, seasonal cycles. For example, when Social Security checks came out, that was always a big demand day, right? So that wasn't really tied to the season, it was just tied to the government calendar. Even times of the day were busier than others, right? Like, if you work for a restaurant, there's a rush hour. That can be considered, seasonal variation as well. So the first two, as statisticians, we're not so bad at long-term trend. We're pretty good at forecasting long-term trend. We're also not bad at seasonal variation because there's a pattern. We can see that pattern. We can see, sales are typically off 30% in February, but they're typically up 50% in November. We can see. The things we're not so good at as statisticians are the next two. So there's 4 components we're going to talk about. The next two we're not as good at. The next one is called cyclical variation. Okay? And cyclical variation is an upturn or downturn, really not tied to seasonal variation. It really results in economic conditions. So you've heard the phrase, the economy is cyclical. So if I'm in office and the economy is up, I don't use that phrase, right? I just say, hey, the economy's up because of me being the politician. But if the economy's down, you bet your butt I'm saying, hey, the economy is cyclical. It's nothing to do with what I'm doing. It just goes up and it goes down. And there's some truth to that. The economy is cyclical. We are going to have another recession, right? We are going to. I don't know if it's going to be this year or next year, but we're going to have one, right? There are cyclical variations in our economy, and a good way to say this is, a rising tide raises all boats, right? So if the economy is strong, maybe our sales went up just because the economy is strong. And if the economy is bad, maybe it's nothing to do with our data, but the economy is bad, so it depresses all sales, right? There's something to that. So we're not as good at predicting that, because if you asked 20 economists right now what's going to happen with the economy next year, they're likely going to be split, right? Their economists are not great at that. Okay? And the last one is the worst one. Okay? We're even worse at this one. The last one is random effects. Random effects are things that we just because data is random. Maybe you usually get, 5 customers an hour at your little shop, but maybe 3 bingo buses just pulled in because they happen to stop there, right? So now, instead of 5 customers an hour, you just got 150 customers that hour. That was a random effect, right? That just happened. We look at enrollment for the School of Business. I'm in charge of the undergraduate. I'm the chair of the undergraduate program. And one year we had, accounting is a good program for us. We typically get about 8 or 9 business freshmen in accounting. One year we had 0. And people would come to me like, what's wrong with accounting? Well, nothing's wrong with accounting. We still have great professors there. It's still a good program. Just random effects, right? We had no accounting freshmen. Unbelievable, right? Unbelievable. We had 0 accounting freshmen. The next year we had 12, and nothing changed, right? It's just a random effect. And eventually some of the people that came as business undeclared went into accounting, but it just happened, right? It's cyclical. Data goes up and it goes down. But we're not good at predicting it, right? We're not good at predicting that. So if we look at this, we try to visualize this. When we talk about long-term trend, when I say stationary, this would be an example of stationary long-term trend. And it doesn't mean it's a flat line, because it's definitely going up and it's going down, but over the long haul, I don't see it trending up or trending down. It's kind of oscillating around a fixed point. That would be called stationary. If I looked at this one, well, I should have said this. So if we're predicting a stationary trend, and we're trying to predict, the next week, well, we're going to try to predict this value, right? The value it's oscillating around. And when it's stationary, if we predict this for week 53, we're going to predict the same value for week 54, and week 55, and week 56, because we're saying it's stationary. So if that's our forecast for next week, it's our forecast for the week after, and the week after, and the week after. If something has linear trend, and that's another one we're going to deal with, that doesn't mean it's perfectly linear. That means it's going up and it's going down, but in general, we can see that it's trending positive. And it's not like an exponential or quadratic kind of, it's trending up and it kind of seems to be a linear trend. So in this case, when I try to predict the future, what I predict for this week is going to be different than what I predict for this week, right? Because I'm saying, hey, it's trending upward. So if I'm predicting 1,000 for next week, the week after, maybe 1,100 or 1,200. So we have to factor that trend in. We also, remember the components of a time series, sometimes we can envision, this has linear trend, but it also has seasonality. How can I tell this has seasonality? How's seasonality indicated here? Because of what? Sarah? Yeah, we can see like a trough here, and it goes up and peaks, and we see that same trough here, it goes up and peaks. So we kind of, and it would make more sense if we label this, and it says, this is January of 2013, and this is January of 2015, right? And we know, hey, January is a trough month, right? We can see that seasonality. So when we predict that, hey, we need to factor in that trend. We also kind of need to, factor in that seasonality. We need to say, hey, it's trending upward, but we know in January or February, whatever it is, it's down 20%. So we're going to take that linear trend, we're going to reduce it down by 20%, right? We want to factor those in. Now, we know that cyclical variation, that's tough, right? That's hard to believe. If you can predict things like that very well, you would be rich, right? If you could predict the next recession, very well, you'd be rich. You could time the stock market, and you would not be in this class probably. So what do we do to forecast? Well, the first thing we want to do, and we're going to kind of go through this step, and we're going to go through it a couple different ways, is we want to identify factors that can be predicted. I talked about long-term trend, we're pretty good at that. Seasonal variation, we're okay at that. Cyclical variation, and also random effects, not so good. So let's try to deal with what we can deal with. So we use a systematic approach. First, we look at the time series and we try to understand it, and we say, is this time series stationary over the long term, or does it have some trend? Because that's going to affect the model I use to predict it. Also, does it have seasonality? Once we hypothesize a form, is it stationary, does it have trend, long-term, linear, positive or negative trend, then we're going to select a forecasting technique. And what's cool is there's multiple forecasting techniques. Okay, so maybe we take, to forecast our enrollment at St. Francis, maybe we take a 5-year average, right? We say, let's take an average of the last 5 years. That's called a 5-year moving average. Or maybe, we just say our forecast for 2017 is whatever it was in 2016. That's a technique. It's called last period technique. Or maybe we use what's called a weighted moving average, where we say, hey, last year matters more, right? What happened 5 years ago matters less, so let's give this more weight than this. And then there's some other techniques that I'll teach. So we select a forecasting technique, and we prepare a forecast. So we'll talk about that. Okay. So I'm just going to do this. So the first thing we're going to deal with are stationary forecasting models. Stationary means over time, it goes up and it goes down, but we're assuming, it's kind of consistent. We know there's deviations in this damn thing, but it's kind of consistent. So the general form of such a model is y sub t, where that's the value of the time series at time period t, is equal to beta sub 0, which is some value, like 50, 100, 1,000, 2 million. And then there's random errors, right? Random errors that we really can't forecast, right? We know they happen, but we cannot forecast them. So let's look at an example in your book. that has a stationary forecast. And it is in your book on page 393. And I'm going to project it up here in a second. So take a few minutes and read that, and then I'll kind of summarize it, and then you guys help me figure out what we're going to do with this. Okay, so to summarize, we have demand for our yo-yo product for 52 weeks, right? And we're trying to predict demand for week 53. So we have Carlos and Bob and Amy, they all have their methods. And we want to determine a method that we can use to forecast our demand for yo-yos for week 53. So first, you remember that first step was we should hypothesize a form. So we first should look at the data and see if we think it's stationary or if it has long-term positive trend or long-term negative trend. So help me do this. How can I do that? Let's pull up the data first, okay? So let's go to the data. The data is, if we go to chapter 7 on Blackboard, and you'll see YOHO data. That's our yo-yo data. And I open that up. And it looks like this. So we have 415, 236. That goes all the way down to 484. So we have 52 weeks worth of data. Now one thing I want to do is, you see how it says compatibility mode? You guys know what that means? This is an old version of Excel. This is like a 2003 maybe file. And I would really like to use all the four features of Excel. So even if you have 2013 or 2016, I'm going to upconvert this thing. So I'm going to go to the File. And you see this convert with an up arrow? That's called like convert it up to the latest version. And it depends on what your version of Excel is. It may say, well, delete and cannot be restored. Just say OK. It might say, do you need to reopen the workbook now? Say yes, or you might have to resave it. But when you do this, you see the compatibility mode goes away, and the file is now XLSX, which is like the latest version, 2013, 2016. Okay? All right, so once again, I want to visualize this data. What can I do to visualize this data? I'm going to do this a little bit different.
Graph it.
Okay, let's graph it. A couple different ways I can graph it, and it's time series data, so a lot of times we'd use a line chart. But what I'm going to use for this example is I'm going to use a scatter diagram. So here's what I want you to do. I want you to highlight A1, the whole way down to B53. And depending on your version of Excel, this may be in different places. But I'm going to say insert, and you have charts over here. And there's one that has little points. I'm going to insert the scatter diagram. And let's use the scatter with straight lines. You can use any one you want, but I'm going to use the scatter with straight lines. Let's issues. If you go to insert graphs, there's one that looks like dots. If you click on, if you want to expand it, say see all charts, you get a list over here. It's like XY scatter. You find it? Okay, so we're going to fix up that chart, and I know that's going to be a review for a lot of you that had me for classes already. But before we fix up that chart, because that's a crappy chart, what do you see with that chart? What do you see, like, what would you visualize about that chart? Would you say it has long-term trend positively, negatively? Or would you say it's more stationary? What would you say? It's more stationary. It goes up and it goes down, but boy, it's not really trending up or trending down. Okay, so let's fix up that graph. And this is, if those of you that haven't done much charting with Excel, Excel does this very, very well. Click off the chart anywhere, and you'll see you have chart tools that go away. And if I click back on the chart anywhere, you see I have chart tools that come back. Excel, very intuitive, knows, hey, you must be monkeying with this chart, so I'm going to give you chart tools. If I go to design, a couple things. I don't have a y-axis label. I don't have an x-axis label. It's not usually a good thing. So I can add those in individually, but there's a quick layout that kind of gives me a template. And I'm going to pick the one that has a title. The layout one has a title. It has an x-axis label and a y-axis label. And you know, I could fix this up then. I could say this is, I don't know, we could just click on the title and say this is yo-yo demand for 52 weeks. Hit enter. This is, I don't know, demand, I think. And it was, I think, in dozens or, I don't know, pallets, I don't care. And this was weeks. And I only have one time series, so I don't need demand, so I'm just going to click on that and then hit my delete key, and it's gone. Also under design, if I want to change the colors, I can do that as well. And under chart styles, you know, this is many different styles. I am kind of a fan of the black and gray background. I think that's a hot looking chart. So I picked style 9, but you can choose whatever style you like. And these kind of things I show you are available for all the charting mechanisms. But we have a chart there, okay? And if I wanted to, you know, change things, I can always use this plus, you know, and I'm not gonna, I don't have time to teach you every nuance of charting tools, but you know, if I wanted data labels, I could check data labels, and now every point is labeled. That doesn't look good. If I wanted to get rid of the title, I could uncheck this and it would be gone. If I wanted that legend back that I got rid of, I could check on legend and you see it's back. You know, so all these things, you know, can be added. They can also be added over here. If I click on the chart under add chart element, there's all those things. So there's multiple ways to do this. All right, so you guys have said stationary. Visually, you've looked at that and told me stationary. But visually is one thing, but I may look at something and say that's a beautiful sunset, and you're saying, yeah, it's okay, right? Because visually, we can subjectively be different. So we'd really like to do this numerically as well. Okay, we'd like to say numerically that this is stationary. So I'm going to show you two ways to do that. One is easier, one is more difficult, and that's what the book teaches. But I'm going to show you the easy way first. So I'm going to right-click on that line or a point, depending on what you added. Right-click. And then I'm going to go down to, you see the Add Trend Line? Yes? Click on Add Trend Line. And it says, hey, what kind of trend line do you want? I'm just going to do linear. See that option button that says linear? And I'm going to check also the checkbox that says display equation on chart, display R squared value on chart. And it gives me a text box. And I'm going to move that text box so I can see it. Okay. What that trend line is, and it's called a couple different names, but it's called the line of best fit, okay? It's also called the least squares regression line. It's statistically the best line that fits those points, okay? That's statistically the best line that fits those points. That's the function of that line. Y is equal to 0.3339x plus 369.27. Okay, that's the line that best fits those points. There's only one line that best fits those points. That's it. Now, a couple things tell me that this is stationary. And a couple things, visually looking at it, that's a pretty flat line. And the way we see that numerically is the slope of that line is 0.3339x. And that's relatively small when we compare it to the values, which are oscillating around, 370, 369, 400. So the slope is relatively small when we look at it according to the values. But the other thing that's probably more telling is the R squared value. Now, the R squared value, and this isn't in your book, so you'll have to write this down, is something called the coefficient of determination. And the coefficient of determination is always between 0 and 1, or 0% and 100%, depending on what you want to talk about. And what it tells us, it says the percentage of the movement of the Y value, which in this case is demand, that has historically been explained by movement in the X value, which in this case is time. So it's telling us 0.0027, so about a quarter of 1%. So time isn't driving this thing. Remember, this is saying the percentage of the movement of this value, which is demand, that is being driven or explained by that value, which is time in this case. So it's telling us about a quarter of 1% of demand is being driven by time. If this was trending positively, we're saying, hey, time matters. Time is driving this up, or time is driving this down. But because that value is so low, and this is ridiculously low, even if it was probably less than 10%, we'd probably call this thing stationary. Right? Because time really isn't, so it's less than 10%, we're going to call this thing stationary. Now, that's one way. That's an easier way for us to numerically say that it's stationary. Another way is for me to actually do the regression. And I'm going to show you how to do that. And this is what your book walks you through. So if I go to data, and do you guys all have data analysis or no? Did we turn that on at some point? No? Okay. So if you go to data and then data analysis, under the list of things, you'll see regression. I'm going to click on regression. I'm going to click OK. And wants to know my Y range. Well, in this case, my Y range goes from B1 down to B53. My X range is my weeks. That goes from A1 to A53. Because I selected row 1 in both those selections, and row 1 contains labels, I need to tell it that by checking the labels box. So it ignores that. If you don't check that box and you put a word in there, it's going to not work. And let's not worry about residuals and normal probability plots, all those things. That's beyond the scope of this course at this point. And I'm going to click OK. And it runs a regression analysis. And some things in here you'll see, you saw already. And there's some things that are new. So one thing we see down here at the bottom is it runs a regression analysis, and we see the intercept is 369. That's the same intercept that we saw in our add trend line. You'll see the slope is 0.336. We also have an analysis of variance up here. We also have a couple p-values. We also have some confidence intervals. All I want to show you at this point is the p-value for not the intercept, but the period. That's the slope, okay? And anyone remember p-values? Or maybe you talked about that in Dr. Timmons' managerial economics class, yeah? Okay. What is a p-value? The p-value is the probability that if we make a claim that we're wrong, okay, if we make that claim. So when we run a regression analysis, we're doing a hypothesis test, and what we're trying to prove is that the slope is not equal to 0. The slope of a line is not equal to 0, meaning that there's some significant slope. If there's a slope, that means it's going up or it's going down, right? The p-value, it says, is roughly 72%. It's saying if we make this claim that this thing has trends, the slope is not 0, there's a 72% chance we're wrong. I don't usually like to make claims where there's a 72% chance I'm wrong, depending on what kind of mood I'm in. Maybe if I'm fighting with my wife, I'll make that claim. But normally I don't, right? Typically what we want here is for us to make this claim, we want a p-value in the statistical world less than 5%. So if that p-value for that slope came out to be less than 5%, we can say, hey, it's statistically significant that this thing has a slope. That's the way the book teaches you to determine, is this stationary or does this have trend? If this thing had trend, you would see that p-value would be a very small number, meaning there's evidence to suggest that this thing has a slope, a non-zero slope. Does this make sense? Now, I'm fine. I want to show you this because if you read the book, that's what it's showing you. But for our purposes, I'm fine with you interpreting this r squared value, which, by the way, the regression also gives you. That's, I don't know if you saw that. There's a r squared value there as well. And saying, you know what, if that r squared value is less than 10%, I'm going to call it stationary. Okay, let's I'm not going to stop there, but let's put a pin in this one. I hate that. I don't know why I said that. I hate that thing. But anyways, let's pause, okay? And I want you to bring up another data set out on Blackboard. And it's at the bottom, and it says MECO monthly sales. You guys see that under Chapter 7? So hopefully, I think that's already in the latest format it is. But I want you to do, with that MECO monthly sales, I want you to do the same analysis we just did together on the yo-yos. Okay, so I think we have 24 months worth of data at MECO sales, MECO company, where I sell things. So do the same analysis on this, and I want to see if you see a difference. You do the graph, do the trend line, do the R-squared value, do the regression. So if I highlight the data, I do insert, do scatter, I'll do the smooth lines. You guys know I could fix that up. I could, add the labels to it. Visually looking at this though, I can definitely kind of see, a positive trend, right? Definitely see it visually. Let's right click on it, do add trend line, linear, display equation on chart, display R-squared on chart. And we see a couple things. First off, the slope of that line is not negligible when we compare it to the y-intercept. 920 is not negligible when we compare it to the values. So that's telling us that, hey, this thing has some slope to it. We also see an R-squared value, a coefficient of determination, of roughly 90%, which is telling us, 90% of the movement of cells can be explained by time, right? Time is driving this thing, and it's driving it, in this case, upward. If I do the regression analysis that I asked you to do, now we got a data analysis, regression, input Y range is B1 through B25 in this case. The input X range is A1 through A25 in this case. The labels, new worksheet apply, click OK. Now one thing I note here, the p-value for the month, which is the slope, the thing driving the slope, is 1.6 times 10 to the negative 12. So it is 0.11 zeros, 4, 5, 6, 7, 8, 9, 10, 11, 1, 6. That is the odds of me saying that this thing doesn't has a non-zero slope and being wrong, right? So likely, very, very likely that this thing has a slope, right? That this thing has a slope, and it does. All right, so all I've done at this point is we've characterized two different time series. We've said the yo-yo one is stationary, right? We've determined that. The MECO monthly cells is linear. We're going to take a 10-minute break, come back at 10 till 8, and we will now predict using various forecasting models for stationary and linear. So hold on to those for a few seconds. All right, so what we learned before the break was, how we look at data graphically and numerically to determine, does this thing have long-term trend? And what we're going to do now is, now that we know, so the first one for the yo-yo data, I know that it's stationary. So I'm going to look at some different techniques that we can use to forecast stationary data. And the first one, you don't need to pay over $2,000 for this class to use this technique. It's called the last period technique. So all we do, and this is a valid technique that's used in a lot of places, we say, what was our forecast for this week? Well, what was our demand last week? And that's, a lot of places use it and use it well. So that's called the last period technique. Our last data point is my forecast for my next data point. Simple as that. That has some weaknesses in that, hey, it only uses the last period technique. So we may be able to improve that by using something called, a moving average, okay? And the moving average, and you can look at the math if you want or don't need to, the moving average is just an average of the last so many observations. So we might use a 3-week moving average where we average together the last 3 weeks, a 5-week moving average, a 10-week moving average, but a moving average, just average the last, and you see this a lot with, stocks, what's the moving average been doing, not just where it's at right now, but how's it trending, the moving average. So we'll talk about that technique. Moving average. There's also a technique that says, what happened last week, or maybe last month, means more than what happened 3 weeks ago or 3 months ago. So I want to use a method that gives more weight or more credence to more recent values. And I still want to use a moving average. I still want to use maybe the last 3 weeks, but I want to use what's called a weighted moving average. And a common one that's used is a 3-period moving average, weighted moving average, 3-period weighted moving average, where we give 60% of the weight to the last period, 30% to the one before that, and 10% weight to the one before that. So 60, 30, 10 is a common approach to that. 60% of the weight goes to last week, 30% to 2 weeks ago, and 10% to 3 weeks ago. Those weights, a couple rules with those weights. They always are between 0 and 1. They have to add the 1. And they should logically be descending, right? We're going to give more weight to more recent values, right? What happened this year is a better predictor than what happened 3 years ago. So that's why the weights go down. And then finally, the last one. Okay, so the problem with, so there's 4 techniques: last period technique, the plain old moving average, and the weighted moving average. And the last one, okay, is the drawback of these 3 are they only use, we have 52 weeks worth of data or maybe 3 years worth of data. These techniques only use the last so many, maybe the last period, the last 5 periods, the last 3 periods. So there's a method called, where is it at here? Okay, it's called the exponential smoothing technique, okay? And it is an iterative technique that uses all the values. And I could probably explain it more when I show it to you. But all the previous values of historical data affect the forecast. So it uses, if we have 52 weeks worth of data, it uses all 52 weeks worth of data. And it smooths that data. Smooth that data means, maybe the data was very rocky. It went up and it went down. It tries to follow the average, but it tries not to react abruptly to those changes. So it smooths it. I'll show you that in a moment when we take this Yoho data and forecast it, okay? So there's 4 techniques. Last period technique, which we don't really need to do much with that. That is just whatever it was week 52, that's my forecast for week 53. Moving average, maybe a 3-week moving average or 5-week moving average. Weighted moving average, and finally exponential smoothing. So let's do this for this Yoho data. So I'm going to go to Blackboard, and you're going to like the fact that under material by chapter, under chapter 7, we have another template, and the one template we have is called forecast template. And you'll see it's a workbook that has multiple worksheets. And I'm going to go to my Yoho data, and I'm going to copy that data. So I'm going to take just the data part. I don't want the title, but I do want the period and the demand. So I copied B2 down to B53. And then I'm going to go to my forecast template, and I'm going to copy that into A11, or paste it in. And we don't have what would my forecast for week 53 be if I use last period technique? 484, because week 52 was 484, so my forecast for week 53 is 484. What would my forecast be for week 54 then? Because it's stationary, 484. For week 60, 484. If I'm saying this damn thing is stationary, well, that's my prediction. Okay? Now, this tab is simple moving average, so I copy my data in A11 down to the bottom, and I need to tell it how many periods I have. So I have 52 periods. I'm sorry, in the moving average, I'm going to say, let's do a three-week moving average, and 52 periods worth of data collected. So 52. God bless you. So using a 3-week moving average, what it's going to do is going to take 484 plus 482 plus 393, average them together, and it's telling me my forecast for week 53 is 453. So last period technique, remember we said 484. Using a 3-week moving average, we said 453. You guys with me? Yes, no? What's wrong, Joe?
I got lost.
Where are you at, though?
Well, I got the numbers of it.
Okay.
Where you see the-
So you have this number. Do you have all these numbers on here?
Yeah.
Okay.
Yeah.
Did you put 3 into number of periods in E2? Are you on the simple moving average tab first of all?
Yeah, I have all the numbers you have, I just missed.
Oh, okay, that's easy. We are saying for this, we're using a 3-week moving average. We're saying the forecast for period 53 is 453. Because we have 52 weeks worth of data, we're trying to predict week 53. So we're saying 453. I don't have a template for this, but if I were using the last period technique, okay, which is a valid technique, my prediction would be what? Because week 52 was 484, my prediction for week 53 would be 484. Does that make sense? Now, I wanted to use a weighted moving average. So I'm going to take that same data, and it doesn't fill in, I should make it fill in, but I'm going to copy that data, and I'm going to go over to weighted moving average. And I'm going to copy it into A12 this time. And I'm going to say, all right, we're going to use a 3-week moving average. So I'm going to put a 3 in E2. I have 52 weeks worth of data. And this one wants to use weights. So we're going to give 60% to the most recent value, 30% to the one before that, and 10% to the one before that. So what this is doing, I'm going to spin down to the bottom, It's saying take 484 times 60% plus 482 times 30% plus 393 times 10%. So instead of all three of those values getting equal weight, which happens in an average, we're giving more weight to more recent values. Does this make sense? That's what a weighted moving average. Let's move on. Okay, so let's take that same of data, period 1 through period 52. I'm going to copy it. And I'm going to move over and copy that into exponential smoothing tab. I'm going to copy that into A9. And I'm going to say 52 periods worth of data in E2. Now this I haven't explained yet. We have a smoothing constant, which is using the symbol alpha. This smoothing constant is always between 1 and 0. And I'm going to start out with, 0.10. Okay, so 10%. And I want to show you what's happening here. Okay? This one, and it makes more sense when you see it, this one starts at the very beginning. So it is saying if I were going to predict week 3, okay, I'm going to use week 2's results, okay, and I'm going to give 90% of the weight to the forecasted value and 10% of the weight to the previous value. So it's taking 90% times 415 and 10% times 236, and you got 397. If I'm predicting week 4, I'm going to take 90% of 397 plus 10% of 348 and get 392. If I want to predict week 5, I'm going to take 90% of 392 plus 10% of 272. So what it's doing, I don't know if you can see this, if I use a small smoothing constant, like 0.01, you see that forecast value, which is an iterative thing, it's going the whole way down, it's not changing a lot because it's highly smooth. Because in this case, 99% of the weight is given to the forecasted value and only 1% to the value itself. If I use a high smoothing constant like 0.99, you see it's roughly following the previous value. It's saying, my forecast for week 3 is 237 because I'm given 99% of the weight to 236 and only 1% to 415. So the smoothing constant determines how much do I follow the value and how much do I smooth it. Does that make sense? How much of the weight is given to the value and how much weight is given to the forecast. And it depends. So if you see, if I use 10%, it gives me a forecast for week 53 of 392. If I use 90%, it's 482. So it's dramatically different, right? But that's what the smoothing constant do. Smaller smoothing constants mean the forecast is more smooth. And it is an iterative process. It starts at week 1 and goes the whole way down until it gets to week 53, and that's my forecast. So it uses all the values. Okay, it uses all the values. I'm going to go back to 10%. Okay, I'm going to go back to 10%. And we'll see it's 392. Now this is what I really like about forecasting. So I used 4 techniques. I got 4 values. Last period technique, I said 484. Simple moving average, 3-week simple moving average, I said 453. Weighted moving average, I said 474. Exponential smoothing, I said 392. Which one's better? What could I do to determine which one's better? I only can do one forecast. My boss, she's not going to be happy if I go to her, she asked me for a forecast, and I say, well, here's 4. She's going to say, which one should I use? Yeah. We just did that in our head. Last period technique. We just used the last period. And week 52 is 484. So that's where I got 484 for. Okay, we don't need they didn't build a template for that because it's just the, last period. Okay. So how can we determine what's the best one? I want to point something out. As I plug in those numbers, some things populate. Even though I'm trying to predict week 53, right? Simple moving average. And I'm using a 3-week moving average. All it's really doing is looking at week 52, week 51, and week 50, adding them up and dividing by 3, and figuring out a forecast. But it seemed to do all that work as well beginning in week 4. In week 5, it forecasted week 4 and week 5. I don't care about, that's in the past, right? That's in the past. Why do I care about what my prediction was in week 4 and week 5 and week 6? I'm at week 52 right now. Why do I care? How could I use that? Damon?
If you could see how accurate the forecast was previously.
I could pretend, right? I can pretend that it is end of week 3 and I'm predicting week 4. If I were to use this method back at the end of week 3, what would I have predicted for week 4? I'd have predicted 333. But what's beautiful about this is it's not really the end of week 3, it's the end of week 52. So I can say back in hindsight, right? In hindsight, well, I would have predicted 333, and the actual value was 272. I would have been off 61. I would have been too high 61. If I'd used this forecast in week 5, I'd have been off 5. And if I used it week 6, I'd have been off 95. And if I used it week 7, I'd be off 122 and 60. So what's nice is I can say, historically speaking, if I use this forecast, what would happen? So I have a couple things. These are called performance measures of forecasting techniques. I have the error, which is just, as you can see, I'm subtracting the value minus the forecast. And because that goes up and down, I have the absolute value of the error, right? So the absolute value of negative 61 is 61. And then I have a column that says square the error. And when I square something, what happens to it? When I square something, it always becomes positive, and it also amplifies, right? And I have the percentage error, the absolute percentage error. So I was off 61 when it was 272, so I was off 22%. Here I was off 5 when it was 280, I was only off 2% roughly, right? So I can go back, historically speaking, and look at all these forecasts that I would have made if I used this method and say what the error was, the absolute error, the error squared, and the absolute percentage. But still, that's a lot of data, right? That's really, 48 weeks worth of errors. I want to get my mind around those errors. So great, statistics can help me do that. Up here along with the forecast, we have 4 performance measures of that forecasting technique. Let me go through, I'll go through all of them, but we kind of focus on one because I like one more than others. The MSE is the mean squared error. So the MSE is the average of this column. So historically speaking, the average squared error was 12,466 if we use this technique. The MAD is the mean absolute deviation. On average, this technique was off 92. That's not great, right? The MAPE is the mean absolute percentage. We were off 26% on average if we use this technique, historically speaking. The LAD is the largest absolute deviation. The worst case scenario if we use this technique, 1 week we were off 274. That's the largest absolute deviation. So I can go to my boss and I could say, if we use a 3-week moving average, historically it's been off roughly 27%, 26%. If we use a 3-week moving average with these weights, it's been off 28%. That's not great. If we use exponential smoothing with a smoothing constant of 0.1, we've been off 25% on average. If I were choosing between these three techniques, and I was using the MAPE as my determining factor, which one would I use? The simple moving average, which is roughly 26.8%. The weighted moving average, which is 28%. Or the exponential smoothing, which is 25%. I would use what? Sarah? Smoothing. Because historically speaking, it has the least error. Now, I can tell my boss then, I can say, you know what? Using this forecasting technique, I'm coming up with 392. But let me warn you, historically speaking, it's average, it's been off 25%. That's pretty crappy, actually, for a forecasting technique. That's because the data they gave us goes up and down. It's pretty violent data. That's why none of these forecasting techniques are pretty good, because it had a lot of variability in it to begin with. But we can historically tell her, this has been off like 25%. So, say my estimate is 1,000. I know it's not. I could use that 25% to say, you know what? It's 1,000, but maybe it's been off 25%. So maybe I can give you a range instead. Going up from 750 to 1250 is my estimate. Okay, so we can use it that way. A lot of times when we're dealing with data, when the data is not as variable, a lot of times we get MAPEs of around 5%, which isn't bad, right? That's not bad. And if we play around with some of these things, maybe we can get better. Well, at 10%, it's 25% MAPE. Let's see, at 25%, oh, it got worse. What if I do 0.05? I don't know, did it get better? It wasn't a big change. Yeah, it looks like that's better. Do 0.11. Yeah, it looks like that's worse. Do 0.09. I think that was better than 0.10, wasn't it? Yeah, I think 0.09 was better. So I can do that by hand, try to pick the best smoothing constant to use historically. But why should I do that by hand? What do I have that picks the best for me? Yeah, we've used the hell out of it, right? So I could go in here and say, think about it. I can say data, solver. I can say, hey, solver, you're allowed to change. Oops, I'm sorry. Your objective is, we'll take J3, which is our MAPE, and I want to minimize that. I want to make that as small as possible. And you're allowed to change the smoothing constant, which is E3. And the only constraint I have is that smoothing constant has to be between 0 and 1. So I'm going to say, I'm going to add a constraint that the smoothing constant, which is E3, has to be less than 1. And it also has to be non-negative. I click solve, and it finds a solution for me. It says, historically speaking, the best smoothing constant to use for this data is 0.06181. And it's unique to this data, the way this data works. 0.99 is going to be worse. 0.87 is going to be worse. 0.1 is worse. 0.12 is worse. So we're taking things we learned in the first part of the class and looking at them here. Okay. Let's do the other one. Okay, so let's go to the MECO monthly sales. And in truth, what we do for anything that has linear trend, which is awesome, is the regression line is our estimating engine, right? If we say this thing has positive linear trend, well, we have an equation that is that line. It says y is equal to 920x minus, let's just call that 200. So if I'm trying to predict I think we're in week 24, if I'm trying to predict week 25, how would I predict week 25? What would I do? Remember, X is weeks, Y is demand or sales in this case. If I want to try to predict week 25, what would I do? Plug 25 in there. Plug 25 times 920 minus 200, boom. That's my forecast. If I'm trying to predict week 100, what would I do? I'd plug 100 in there, yes? That is my forecast, right? Now, you can as well, I'm going to copy the data, so 1 to 24. You'll see in my forecast template, there is a tab that says linear regression. And I can copy that data into A12. Tell it I've picked up 24 months of data. I had to make that column wider. And it tells us what the prediction is for week 25, week 26, week 20, or these are months, I think. Like the next 30, next year. And if I want a specific month, it only gives you, it looks like, what, 12 of those, or 10, 11, 12, yeah, 12. If I want like period 50, I can put in 50. And it'll give me my forecasted value. All that is doing, however, is using the regression line. Now, what's awesome about this, okay, we've been talking about time series forecasting, so taking data that has been given over time to forecast. But in the business world, it's not always just data over time. Sometimes, I beat the hell out of this example, but if I run an ice cream stand, okay, and I want to predict sales at my ice cream stand. Well, I know, I'm closed. I'm only open in the summer months, so I know it's seasonal, but I'm smart. I don't open in January. How can I predict my sales for next week? What would you use to predict my sales for next week? Time is probably less important than this other variable. What's the other variable that's more important?
Weather.
Yeah. So if I know there's a heat wave coming, right? I'm going to make sure I have a lot of inventory, make sure I have people staffed appropriately, all those things, yes? So what I could do is maybe I had last year, right? And I had, what was the high temperature that day? And what were the sales that day? And that could be my scatter diagram. And now I can do a regression analysis that relates what? Relates temperature to sales, right? So Y is now sales, X is temperature. I plug in the high temperature, what I expect it to be the next week or the next day. That will estimate my sales, right? And then I can staff appropriately. I can have appropriate inventory. Another good example, has anyone ever sold or bought a home that they had it appraised? Anyone have a home appraised ever? What's the first thing they feed into? There's people that are trained to do this. What's the first thing they feed into that?
Comparable.
They feed in comparables, right? So what are they gathering? They say, in your neighborhood, there were, in the last 2 years, 10 homes sold like this. And they look at it and say, well, square footage is a big determinant, right? So this was a 1,000 square foot home. It sold for 200,000. This is a 2,000. One would say sold for 400,000. They build a regression analysis between square footage in this neighborhood and what? Selling price, yes? That's their starting, and that they plug in, hey, this is a 3,000 square foot home, so we're starting at 500,000, but then they do what? Because it's part science and part art, they adjust up for things. They say, well, this one has a swimming pool, so maybe they adjust up. This one has quartz countertops, and this one, the Mikos live next door, adjust down, things like that. They adjust up, right? They look at things you can't measure in those comparables, and they adjust up and down. But it's regression analysis, right? That's what you do. And Eric mentioned, our enrollment, okay? I can tell you, I did this analysis for the university, I think it was about 7 or 8 years ago. There are two variables that drive our freshman enrollment at St. Francis University. Our admission staff is awesome. Enrollment management staff is awesome. They do a good job, but there's two variables that drive the change. The R squared value is like 90% if we factor in these two things. What do you think the two things are that drive, not just us, but almost all, non top tier like Harvard, but small liberal arts, privates, not liberal arts, but small private colleges. Two things. What do you think those two things are? Go ahead. Yeah, so what's awesome is we know how many seniors there are, right? So about 10 years ago, St. Francis had record enrollment. Every year we had record enrollment. But then so did the Mount Aloysius, and so did Juniata, and so did St. Vincent, and so did Penn State Altoona. Why was that? Is it because everyone's doing a great job and, because, did you ever hear the baby boom echo? There were more inputs, right? There were more potential customers, so we had more, right? What else? So you're right, the number of high school seniors matters, right? And right now it's tough sledding out there. What else matters? Especially for a private school like St. Francis University. It is not like, we have a great reputation, but not, some people are immune to this because they have like a Bucknell reputation, right? Okay, like how much we like price matters. So how much we discount matters. So those two variables are huge, right? Those are huge. So we might not be able to control there's people much smarter than me trying to figure this out, but we may not be able to control the high school class size, right? That's just, things, but we can control how we discount, how we do those kinds of things. But there's all kinds of things like that, right? There's all kinds of things. If you can relate a variable you know very well to something you want to know through regression analysis, great. You have a prediction engine. You can go from, no knowledge to something you know. And even if it's not perfect, it is still very, very powerful stuff. Okay? So we focused on time series, where time is the X variable. Time is the thing we're trying to relate to the forecast. But that variable could be a lot of different things, right? If we think about when you were undergraduates admitted to your college, they tried to predict how good you were going to do at that school, like academically, how well you were going to do at that school. What did they use to predict how well you were going to do at that school, whatever school you went to undergraduate? SAT, those are the independent variables. And even when you combine them, okay, when you use both, the R squared value, the coefficient of determination, I don't have it up there anymore, is only 36%. So meaning only 36% of how well you do in college, GPA-wise anyways, can be explained by how well you did in high school and your SAT score. So that means 64% is explained by other things like what? No. Things that are harder to measure, because entrance exams are kind of like SATs. What's harder to measure? That impacts a lot of freshmen, because I see it every damn, Sarah Price sees it now every damn day. Yeah, like maturity, your work ethic, how much you're going to deal with not having your mother lay out her clothes and wake you up every morning. That's the maturity, like those kind of things. Are you going to go wild in college because it's your first taste of freedom? Or some people go the other way, right? They say like, I was kind of screw off in high school, but this is a chance to be a new person, and they do better, right, than we predict. So those two things are the best predictors we have, SAT and high school GPA, and that's what colleges use. They use those a lot, but they also do personal interviews and look at extracurriculars to try to fill in those gaps. But that is only can predict 36% of the movement of GPA, which, but still that's the best we have. So a lot of these variables can come into play. I know, tangential there, sorry. Here is what I'd like you to do for homework then. And okay, when you do this homework, there's data in the book, and it's written in the book, okay? But don't retype it. You'll see under chapter 7, like for problem 21 and 22 I'm assigning you, that's the data file. It says data burger, so, or data for the burger. data for Sablet. So just use that file, right? Don't retype the data. So what I'd like you to do for homework in chapter 7, I would definitely like you to do 1 and 2. Let's see. 21 through 23, that's good. They're all related there. Do 30A. You don't have to worry about B. And then 31 and 32. 30A and 31 and 32. All right, that's all I have. So have a good night, have a good week. I'll see you next month, November.